As another application, which is quite important, I would like to talk about quite briefly about algebraic coding theory. While coding theory is a vast subject, and there are other methods apart from algebraic coding theory, which we are not, of course, going to go into. And with algebraic coding theory, we are going to even do a very elementary introduction. But you see, these very abstract concepts have very real applications. This is one example I would like to show you. Error detecting and correcting codes are of utmost importance both in communications and also in data storage. If you do not take any precautions like error correcting codes, even a single bit error may corrupt your data, and this can be very expensive in a number of ways. For instance, a very simplistic approach is using a parity bit. Okay, assume this is your data consisting of 7 bits, and assume that we use an even parity. Here, in fact, we are using the Boolean ring with the operations addition as exclusive or, and the multiplication operation is AND. So the parity check is performed how? You just add all the bits. And when I say add, I'm meaning exclusive OR, because that is the addition in a Boolean ring. So you get 0, 1, and because it's associative, I can do it in any way, and then this one, and then this one, and then this one, etc. This is effectively counting the number of ones, because I have 3 ones here. That will be equal to 1 because it's odd. Therefore, to make it an even parity, I would like to add another one here at the end as a parity bit. So this indicates in the original data, since this is a 1, in the original data, you should have an odd number of ones, okay? But this is algebraically how you represent it in the Boolean ring. Addition corresponds to XOR, multiplication corresponds to AND. Assume this bit has an error, whether in storage or in the communication channel, depending on your application, doesn't really matter for our purposes here. Assume that this bit is corrupted, it becomes a 1. And how do you check whether it is in error or not? You just add all the bits up. This with this, this with this, etc. And you would get at the end a 1, which will indicate that there is an error. So with this code, this is a parity check code, okay, we detect the error, but we cannot know which bit it has occurred. Okay, so we cannot correct the mistake. So to be able to correct errors, you have to do something more. You have to carry more information to understand which bit has the error. For instance, consider this repetition code. Assume again your data is given in here, 001, 001, 10. As a simple solution, what you do is you repeat every bit 3 times. Okay, so you'll have sort of a majority vote when you would like to understand what the real value is. You repeat each bit 3 times. This corresponds to this 0, this corresponds to this 0, this corresponds to this one, and so on. Now, what you apply here is what we call maximum likelihood decoding. Assume that you have this corrupted message here. Okay, you see you have actually 4-bit errors, but of course what we focus on is on single bits here. So in this chunk we don't see any errors because all of them are the same, so we interpret it as a 0, which is correct. And this one, 0 1 0, it's not in my code. I just have 0 0 0 and 1 1 1 in my code. So is it this one, 0 0 0, or is it 1 1 1? Again, we apply here maximum likelihood decoding. What this means is it more likely that the original was 000 and then an error turned this into 010, or is it more likely that it was 111 but then by two errors it became 010? Here we have a basic assumption. We assume that all bit errors are independent and they have small probabilities. Okay, we assume the probability of a bit being in error is low. So in a general sense, having multiple errors is less likely than having a single bit error. So here we apply majority vote. Since I have more zeros than a one, I decide this is a zero. Okay. Similarly here, I have 1, 1, 0. Since the ones are in majority, I decide this was a 1, which was correct. But look at this one. Here I have 2-bit errors. I detect the error because 101 is something I do not expect, right? It should have been either 000 or 111. So I understand there is something wrong here, but when I correct it, I do it incorrectly because the majority is now in ones. So I decide that this is 111. However, you see the original was 000. So I made a mistake here. So this indicates the capacity of this code, the error correcting capacity. You cannot correct multiple bit errors using this code. You can just correct single bit errors because then majority votes will be incorrect. For instance, if 000 becomes 111, then I do not even know that there was an error here. I cannot detect 3-bit errors. I can detect 1-bit and 2-bit errors, but I cannot even detect 3-bit errors. Okay, so I'll just decide this is the correct message as a bit of 1. Okay, so here we are able to correct single bit errors, but this is clearly inefficient because let's say this is a communications scenario. I'm wasting 2/3 of my capacity. For a single bit, I'm sending 3 bits, so it's a hugely inefficient scheme. The question is, can I do this in a better way?